If these balls are not moving, their velocity is 0.
Yeah.
They all have the same mass, right? And in comes this ball, and it strikes it. What do you think is going to happen after? This is kind of the before picture.
The ball on the far right will move.
You think the ball on the far right will move, huh? All right, well, why wouldn't the after picture look like this? These 5 balls moving with some, V final.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, today's lecture is on kinetic energy. However, this is a term that would have been unfamiliar to Newton. It was kind of a newer concept, and they didn't come up with the term kinetic energy until later. But they were interested in this quantity of motion, right, that you might think of in the following. Right here we have a speeding car headed towards a brick wall. It crashes into the brick wall, the bricks go flying everywhere. So is this just a conservation of momentum problem? Right, because now we've got not just a ball, getting hit by another ball. This is, mortars, the mortar holding the brick together, breaking, the crushing of the hood of the car, right? And so the question is what is the oomph that this car possesses that allows it to do all of this damage? Now, Newton had speculated that the oomph, as we might call it, was proportional to, that's a terrible proportionality, let's try it again, was proportional to the velocity, right? Whereas others thought it might be proportional to the velocity squared. Now, Émilie du Châtelet, who was basically the girlfriend of Voltaire, but an important scientist in her own right, making her own contributions, had heard of an experiment that might actually settle this issue. And this experiment involved dropping steel balls into clay. And so we can imagine that if we drop this steel ball from some height h, right, into the clay, so this is kind of the before picture, but after, what they found was that I just draw it like this. We don't really need this line here, do we? Find that the steel ball would embed itself, would dent the clay, right, creating a hole whose size we'll characterize by a depth delta x. Okay? And so what they found was that the delta x was proportional to the height that you dropped the ball from, but that it was proportional also to the velocity squared. So if you dropped the ball with twice the velocity, it would make a hole that was 4 times as deep. Okay, if you dropped it with 3 times the velocity, it would make a hole that was 9 times as deep.
Okay. So
this seems to settle the question that this oomph that causes the damage, right, this hole that it makes in the clay, is proportional to the velocity squared. Right, let's have a look at what's going on in this situation just a little bit better here, right? You might recall that from lecture 6, right, we had an equation that would allow us to figure out what the velocity is just before it hits the ground if we drop it from a height h. And so this would say that the final, let's call it, we want to get a velocity here too. So I'll just call it v final squared equals v initial squared, which is 0, right? 2 times gravity times h, right? This was that equation from lecture 6. I'll write it up here. So v final squared equals v initial squared plus 2 times the acceleration times delta x, the displacement.
Okay.
So here our displacement is h. We drop it from a height h. We can expect that its velocity, right, is going to be proportional to the square root of 2 times g times h. Now, in order to get this result, it turns out you have to assume that the force that the clay exerts on the ball, so if we do a free body diagram of the ball as it's impacting in the clay, there's going to be an upward directed force, we'll call it F sub c, but it's a constant, okay?
Okay.
Of course, we'll also have, mg acting in the opposite direction, but we can assume that mg is, actually the way we usually write this is as follows, that this constant force that the clay is exerting on the ball when it impacts makes gravity negligible, okay?
Okay.
So if that's the case, then the acceleration that the steel ball will experience, remember that force is equal to mass times acceleration, this will be F sub c over m, where m is the mass of the steel ball, okay?
Okay.
Now, when it first enters the clay, it has this velocity here. I'm going to just call this v squared, okay? Actually, I'm going to call it v I squared because it's the initial velocity in the second step of our problem here, right? So, and then at the end, it comes to rest, so it's got a velocity of 0. So we could write that 0 is equal to this initial velocity, which is in the negative direction, minus vi squared. The force F sub c is upward directed, so we'll have plus 2 times this acceleration, which is Fc over m, times delta x. So this says that vi squared is equal to 2 times Fc, the constant force, over m times delta x. So you can see that delta x is proportional to the velocity squared as required. But notice that I can rearrange this a little bit, right? I'm going to move the mass over here, and I'm going to divide out the 2 so that I directly get this expression, 1/2 mass times the initial velocity squared equals the constant force times delta x. Okay? And the reason I wrote it that way is because these terms will turn out to be significant. In the next couple of lectures, we're going to develop this a little bit, and we're going to find that this term here is something we call the kinetic energy. Okay?
All right.
And this term here we call the work. Okay? And so we'll see that there's this change. Remember, the final velocity is 0, so this is also a change in the kinetic energy.
Yeah.
So we started out with the ball had this stuff, right? This kinetic energy, right? The oomph.
Yeah.
Just before it entered the clay. And then the clay, interacting with it, brought it to rest. So it came to a complete stop. So the kinetic energy went from this full-on value here to 0. And in doing so, work was done on the clay. The work that was done was the kind of the making of the whole. Okay?
Okay.
And so we're going to develop these concepts of kinetic energy and work in the upcoming lectures. But experimentally, right, this was, I think, the first confirmation, right, that this oomph, or kinetic energy, was proportional to the square of the velocity. Okay? So that would mean that in our car example, if we drive into a brick wall at, say, 20 miles per hour and we do a certain amount of damage, it's probably not a lot. Might not even knock any, it might knock our bumper off, but it wouldn't really knock any bricks loose, I don't think. But if we, doubled or tripled that speed, going 40 or 60 miles per hour, the damage that's done would go up, not linearly, but like the square, right? So if we went up to 40 miles per hour, we'd see 4 times the damage. If we went up to 60 miles per hour, we'd see 9 times the damage. That's almost 10 times the damage, right?
Yeah.
Order of magnitude is a big deal. So, and that kind of fits with our common sense of stuff, right? If you punch your buddy in the arm lightly, that's one thing. But if you punch him with twice the speed, right, then, he's not going to be happy. Because it doesn't just double the pain, right? It multiplies it by a factor of 4.
You want to say that again? About the arm punching?
Well, if I punch somebody in the arm lightly, right, just playfully, hey buddy, pop, right, no big deal. But if I, that he's going to, if I double the speed of that punch, it magnifies the pain by a factor of 4 because the energy went up by a factor of 4.
All right, but the speed was only double.
I know, and this says that the oomph, or the kinetic energy, is proportional to the square of the speed. So if you double it, the energy goes up by 4 because the square of 2 was 4.
Okay.
If you triple the speed, it goes up to 3 squared, which is 9. So 9 times the energy, 9 times the pain. Okay?
Okay.
I think that's all I wanted to say about this particular experiment. I guess you could also show, you could substitute back in here finally, right? This initial velocity, right, you might recall, was also equal to 2gh. So you can also show that delta x, if I replace v sub I squared with this quantity here, right, 2gh, is also equal to this 2fc over m times delta x. and ignoring all the other stuff, you do see that delta x is proportional to the height.
Okay.
So that confirms these kind of experimental findings. Okay.
All right.
That's
Okay.
it. So this lecture is going to be about elastic collisions. Remember, we've already talked about inelastic collisions, right, where objects, like a bullet, is flying through the air, it strikes a heavy wooden block, and goes into the wooden block, and then the block and the bullet move away with some velocity. Or the coupling of train cars, right? We've got a train on the rail, and then another train car, and we slam them into each other, they couple,
Yeah.
right, and then they roll away with some velocity. That was one of your homework problems, right?
Yes, it was.
These problems we can easily solve with conservation of momentum. So today we're going to talk about elastic collisions, right? This is where they don't stick together, okay?
Okay.
And so what I want to consider is what's going to happen if I've got four balls that are very closely spaced to each other, okay? I guess I could draw them closer, but I do want to just make sure you understand that they're not necessarily stuck together, okay?
Okay.
They're not touching necessarily. They're just very close, okay? And then I want to have a fifth ball come in with some velocity. Also, I should point out that the masses of each of these balls is exactly the same.
Okay.
Now, what do you think is going to happen? I'll say these are steel balls. Steel balls are a good source for elastic collisions.
Yeah.
The steel is elastic. You probably are familiar with elastic collisions if you've ever bounced a ball, right? That's elastic behavior.
Yeah. Okay.
So, if these balls are not moving, their velocity is 0.
Yes.
They all have the same mass, right?
Yes.
And in comes this ball, and it strikes it. What do you think is going to happen after? This is kind of the before picture.
The ball on the far right will move.
You think the ball on the far right will move, huh?
The ball's going to hit one. The ball on the left will hit the ball on the other ball, which will hit the other ball, which will hit the ball on the right, which is being blocked by another ball, so it'll start rolling up.
Outside, but
Really? So that's what your intuition tells you is going to happen, huh?
like a swing.
If the ball's
Okay.
enough, it might start, maybe more of them will start moving, but
Right, well, why wouldn't the after picture look like this? Right? Because we know that before, right, our momentum is m times v. So we know that afterwards it has to be equal to m times v. So why couldn't we have afterward these 5 balls moving with some, v final? Why wouldn't that happen?
let me think.
So that in the end, right, conservation of momentum would tell us that if this is the case, then we have 5m times v final, and that has to be equal to the momentum before, which is m times v, initial, we'll call it initial if we'd like. The masses will just cancel,
Yes.
and so this tells me that v final would then be equal to v initial divided by 5. So the 5 balls would move away with 1/5 of the velocity. Why wouldn't that happen?
I'm not sure.
I see. Well, most people, I think, would assume that that's what's going to happen, right? That you drop this ball and you'd slam this ball into these other 4 balls and they would all move away with a much slower velocity. If they're all equal masses, then they move away with 1/5 the velocity, right? This would be how this would conserve momentum, so it should be fine, right? Yeah?
Yes.
It should be.
Okay. Well, as it turns out, your intuition, which is better than I guess mine would have been at your age, is good, because if I demonstrate this with this Newton's cradle, watch what happens.
Like a swinging rope.
Right?
That would still happen even if they weren't hanging.
Sure, that's right. So the motion is pretty much in this plane, right? I'm lifting it up to give it some velocity. So the swinging, we haven't talked about pendulum motion yet, but by lifting it up, I'm giving it some velocity, right? And so in the end, it's colliding in this one dimension, and then of course the other ball will immediately swing up. But
All right.
right?
Yeah.
So this result should be a little surprising. Momentum is still conserved, right? Because in this case, the alternative after picture, right, is that we now have 1, 2, 3, 4 balls sitting still, and 1 ball moving away with velocity v, the same, or v initial, we'll call it v final, right? So v final, v initial are the same velocity, right?
Yeah.
So momentum before mv equals momentum after mv, right? That's fine, right? It does work.
All right.
Momentum is still conserved, right?
Yeah.
Now remember, yesterday we talked about oomph,
Yes.
and we said, well, this oomph, the thing that allows collisions to do so much damage, is related to this term we call kinetic energy, right? Which we'll talk about more in the next lecture. But we said that kinetic energy was equal to 1/2 the mass times velocity squared.
Yes.
So let's look at what that looks like in the before and after pictures here. So in the before picture, the kinetic energy, Ke, is equal to 1/2 mass times Vi squared, right? In this version of the after picture, I guess I could extend this, the kinetic energy would be equal to 1/2 5m times V sub F squared,
Yeah.
which is equal to 1/2 5m. Remember that V sub F was V sub I over 5 from conservation of momentum, right? So that would be V sub I squared over 5 squared, which is 25, which is equal to 1/2. This 5 will cancel. I'll get m here. V sub I squared over 5, right?
Yeah.
This is not equal to this.
Yes.
This is obviously greater
Yes.
because this is just like the old, we'll call this, so we notice that kinetic energy after is equal to the kinetic energy before divided by 5.
Okay.
So we have less kinetic energy after than we do before, even though momentum is conserved. What about here, in this case? Well, in this case, we have 1/2 mass Vi squared, that's before, and then after, it's equal to 1/2 m Vf squared. But remember that Vi and Vf are the same velocity, right, from conservation of momentum, so we can just write it as V.
Okay.
And here, the kinetic energy before is equal to the kinetic energy after. That's interesting, huh?
Yes.
And that will turn out to be one of the big differences in an elastic versus an inelastic collision, is that in a perfectly elastic collision, kinetic energy will be conserved, whereas in an inelastic collision, it will not. You'll have less kinetic energy after the collision than you did before. And we'll reason through it once we talk a little bit more about the work energy theorem and the conservation of mechanical energy. We'll reason through it by saying, well, the kinetic energy you initially had and the kinetic energy that you have after the collision, which will be less, where did that kinetic energy go? It went into things like the noise when the trains slammed into each other. It went into heat, okay?
Okay.
And so we'll learn that that energy is kind of lost. It might happen when you couple the train cars together that they oscillate, right, a little bit. Maybe they're bouncing back and forth. That's a kind of an internal energy that it now has.
Okay.
But that energy will go somewhere.
All right.
But we'll talk more about that later. Now, I want to try to understand this result about what happens to the balls after by thinking about the fact that Newton's laws are time reversible, right? They should work the same if time was going backwards as they would if time was going forwards, right? If we think about that, if we think about, you know, the sun, this is my sun drawing, right? And the earth, right, orbiting around the sun.
Yeah.
If I were to like take some vantage points in space and look at this, right, and see this moving, right, I would not be at all confused if I looked at it and it looked like this, right? If it's moving backwards, right, I'm not going to notice
Okay.
because I don't really know what backwards and forwards looks like in a situation like this, right?
Yeah.
That's what you could call Newtonian time if you want to, okay?
Okay.
But you can't tell if things are going backwards and forth. If I make a movie of the Earth orbiting the sun, and you see it going like this, right? You don't have, nothing tells you, oh, that's wrong. That doesn't seem to be right, right?
Yeah.
It would look fine if I reversed it, if I tricked you and I said, well, I'm just going to run the film backwards, right? You wouldn't be able to tell that Newton's laws are violated or something like that, right?
Yes.
You know, contrast that with if I took a video of clouds forming in the sky
Yeah.
or a puff of smoke.
Yeah.
You could see it coming from a very dense puff of smoke and diffusing out, right? But if I showed you a video of smoke being very diffuse and then coming back in and concentrating in the center, you'd be like, well, no, that's not right. Somebody's running the film backwards.
Yes.
Or if I took a video of a guy sliding a block across the table and then reversed it, and the block is sitting still at first, and then it starts moving, and lands into the guy's hand, right? You'd be like, well, that's somebody played the film backwards.
Yes.
Right? This Norbert Wiener called Bergsonian time, and the difference is that energy is conserved in Newtonian time, right?
All right.
Whereas in these other systems, energy is not conserved. It gets much more complicated, and we'll talk about that when we talk about thermodynamics, okay?
Okay.
But for Newton's laws, anyways, it doesn't matter which way time goes, right? So if I played you a movie and the before picture looked like 4 balls moving, and then it resulted in 1 ball moving, you would know which, and then I played it the other way around, maybe from a different vantage point.
Yeah.
So let's go back to the Earth-Sun picture, right? I look at the Earth-Sun picture from above, I see the Earth orbiting around, let's see, like this, right? Well, if I switch my vantage point and I now look at it from the other side, it would seem to reverse direction, right? So I don't know if I just move the camera from one side to the other or not.
Yes.
Whereas you would be able to tell if 4 balls were moving at first, and then 1 ball started moving after the collision, versus 1 ball moving at first and then 4 balls after the collision, because you'd be able to tell which one was first, right?
Yes.
From time reversal symmetry, we can't tell the difference between the 2 pictures. So what would we expect if instead of having 1 ball come in, what if we had 2 balls coming in at a constant velocity and impacting these 4? What do you expect to happen? What's the after picture look like? After.
I don't know why it would look much different.
Well, what do you mean much? What would it look like? What would I see after? What do I draw afterwards?
The ball on the right moving away.
1 ball on the right?
2. There's 2.
Is it 1 or is it 2? Which is it?
2. Yeah, 2.
I know I need to take a ball away from here since this only has 5 balls. So we have 3 balls initially, 2 balls bump into 3 balls. What does it look like afterwards?
2 balls start moving away.
Moving away with the same velocity, right?
Yes.
That's what should happen based on this time reversal symmetry picture that I gave for you, right?
With the same velocity
With the same velocity, yes.
as the 2 balls were moving
It has to be, right? Because if we have 2mv is the initial momentum, the final momentum, if we have 2m,
Yeah.
it needs to be 2mv, right? Momentum has to be conserved, okay?
Okay.
So let's see what happens, right? So we grab 2 balls this time. And that's what we see, right?
There's 1 ball in the middle.
Well, this is, periodic, but it's going to bounce back and forth and back and forth and back and forth, right? And we'll talk more about why it's doing that later, right, when we get to our talk on conservation of energy, okay?
Okay.
But I just want to worry about the first collision, right? So in the first collision, when I drop the 2 balls from the left, these 2 balls that were initially moving and the first ball they come into contact now stand still while the final 2 balls shoot off with some velocity, right?
Yes.
And so that's what we see here. And if we looked at, conservation of energy, that would all, if we looked at the kinetic energy before and the kinetic energy after, we would see that those are equal as well, right? Because if the velocity is the same, then 1/2 2m v squared equaling 1/2 2m v squared, where v is the same, right? We see that works as well.
Yes.
Okay, so with that said, let's talk about more complicated collisions, or collisions in general that are elastic. And I'm just going to take a second to move this out of the way. So now I want to consider a general problem, right, of some m1 v1 all initial. Maybe I'll distinguish initial and final by putting primes on it, okay?
Okay.
And I'm going to allow for the first ball to have some velocity initially as well. So we'll call this m2 v2. And this is the before picture, right? v4. And then the after picture, we don't know what that's going to look like, but it will also have some balls moving in some direction, right? This will be m2, well, the mass is not going to change, but v, oh, not 2, v1, v1 prime, m2, v2 prime. So those are the velocities after it's all said and done, okay?
Okay.
And if I do conservation of momentum, so let's look at momentum. This would say that m1 plus v1, m1 times v1 plus m2 v2. That's the momentum before.
Yeah.
And it has to equal the momentum after. m1 v1 prime plus m2 v2 prime. Okay?
Okay.
But let's do something here that's going to be useful for us in this analysis. Let's subtract like this. Let's do the following. Let's say that m1 times v1, actually I want to, yeah, no, it's fine. v1 minus V1 prime, so I just subtract M1 V1 prime over here, right?
Yeah.
Is equal to M2. This time it'll be V2 prime minus V2, right?
Yeah.
So a little bit of reversal going on there. Now let's look at energy. Or really, let's look at kinetic energy is what I'm really talking about here. So I'm going to write KE. So the kinetic energy before will be 1/2 mv1 squared. Oh, that's going to mess up my primes, isn't it? Well, plus 1/2 mv2 squared, right? And we noticed that in elastic collisions, the kinetic energy before and after were the same, right? So I'm going to impose that condition here, right? This will equal 1/2 m. That should have been a 1, and that should have been a 2. M1 V1 prime squared plus 1/2 M2 V prime or V2 prime squared, right?
Yeah.
Now I'm going to do the same trick that I did here. I'm going to subtract this over so I get a difference in velocities, right? So I'll have, and also I'm going to get rid of the factor of 2, right? I've got a half, a half, a half, a half. I'll just multiply everything by 2, cleans it up a little bit. And I'll have M1 times V1 squared minus V1 prime squared, right? By moving V1, this M1 V1 prime squared over here, right? To the left.
Yeah.
And that will be equal to M2 times V2 prime squared minus V2 squared, right? Just algebra, right? I just moved this over here, so the M1s were all together, and then I moved this over here, so the M2s are all together, right?
Yeah.
You guys remember difference of 2 squares?
Yeah.
So
Yes.
if I have A plus B times A minus B, this will be equal to A squared minus B squared, right?
Yes.
Here's my A squared minus B squared, right?
Yeah.
So I can rewrite this as M1 times, this will then become V1 minus V1 prime times V1 plus V1 prime equals M2 times V2 prime minus V2 times V2 prime plus V2. Yes?
Yeah.
Okay, now here's the cute trick that I'll do, right? Because this is a system of equations, okay? And you don't have to solve it this way, but it makes it a heck of a lot easier, okay? I'm trying to figure out what the final velocities are if I know the initial velocities, or vice versa. If I knew the final velocities, what would the initial velocities be? And I assume I know the masses and stuff, right? But we always have to assume we know some initial conditions, right? So maybe we know the the momentum before, or we want to determine what the state of motion is after.
Yeah.
But nonetheless, it's a system of equations that we have to solve, and we can use both conservation of momentum and conservation of energy to solve this. If we just had conservation of energy, it's not enough information, right? Because if I know M1 V1 before and M2 V2 before, well, V1 and V2 after, that's 2 unknowns, and I've got 1 equation to solve this with, right? I can't solve it, okay? So now for inelastic collisions, the V1 and the V2 were equal, right? They were moving together. So in that case, I could solve it.
Yes.
But if they're not the same velocity, then I can't, okay? But if I have another constraint, this kind of conservation of kinetic energy thing that we've been looking at, right?
Yeah.
That we observed was true with the simple elastic collisions we looked at before,
Yes.
then we should be able to solve it. And so I write both of these equations down. Now I'm going to take this equation, I'm going to divide it by this equation, okay? So if I take this equation, right, so I'll call this equation 2, I'll call this equation 1, then 2 divided by 1 gives me the following. So if I divide this by this,
Yeah.
the M1s cancel, the M2s cancel.
Yeah.
The V1 minus V1 prime cancels this V1 minus V1 prime, and I'm left with V1 plus V1 prime equals. And on the right-hand side, I'll get cancellation as well, okay? The M2 will cancel, right?
Yeah.
The V2 prime minus V2, that'll cancel the V2 prime minus V2 here. And I'll be left with just this term. And so this will equal V2 prime plus V2, okay?
Okay.
Now, that's nice. I can work with that, but if I want to get a little intuition, let me rewrite it just a little bit, okay? And what I want to do is I want to put the initial velocities on one side and the final velocities on the other. Okay, so I'm going to take v1 and subtract v2, because that was the initial velocity of the other one, right?
Yeah.
And that will be equal to v2 prime minus v1 prime. Okay?
Okay.
But I'm going to rewrite that even further. I'm going to take the factor out of minus out of this, right? So it'll now become minus v2 prime plus v1 prime, which I could just write like this. Minus v1 prime minus v2 prime. Okay?
Okay.
Hope I didn't mess that up. Let's just look. Make that positive v2 prime, which it should have been. And that minus, yep, that's fine. Okay? So what are these things? Well, this, do you remember relative velocity when we talked a little bit about reference frames?
Yeah.
If I'm in a car that's going 20 miles per hour, right, and there's a car that's approaching from behind that's going 30 miles per hour, right, the relative velocity between us, right, it doesn't look like it's approaching me at 30 miles per hour because I'm moving at 20 miles per hour, right?
Yeah.
From my point of view, right, my reference frame in the moving car that's going 20, I see this car approaching me at 10 miles per hour, right?
Yeah.
When it passes me, it'll pass me at 10 miles per hour, okay?
Okay.
Right? So this is a relative velocity. It's the difference of the velocities between the two. And so what this tells us is that in these elastic collisions, right, the relative velocity before or of approach, right, is equal to the negative of the relative velocity of recession, right, after they collide. So it says the relative velocity is just simply switch. Okay?
Okay.
Does that make sense?
I think so.
Let's try a really simple problem, right? Which will be an approximate problem. Let's imagine we have a really, let me just work it here, a really large mass, right? This is a big M, and it's moving with some velocity v, okay? And it collides with a little tiny ball of negligible mass, okay?
Okay.
This is the before picture. What about the after picture, right? What happens afterwards? Well, if this is a really big, heavy ball, we can assume that its velocity is going to still be v. Afterwards, right, this is going to still be moving with approximately a velocity of v, right?
Yeah.
Because it's big and heavy, right? This little ball is not going to slow it down much.
Okay.
We'll say that the amount that it slows down is negligible, right?
Yes.
What's the speed of the little ball now, though, right? The velocity of this large ball is going to be approximately the same as it was before.
Yeah.
So if we plug this in, initially, right, v1 was 1. Well, I guess we just call it v. And, well, let's give it a number. It makes it easier. Let's say it's going at 1, and so then it's going to recede at approximately 1, okay?
Okay.
So initially we had 1 meter per second, let's say, minus 0 because it wasn't moving, v2 is not moving. And this will equal minus 1 minus v2 prime. So what is v2 prime? All right, we'll distribute the negative sign. That'll become 1 plus v2 prime. Let me make a sign error here somewhere.
You probably did.
Give me a second. No, I just didn't distribute that right. It's minus 1, because minus times 1 is minus 1, right? So that gives me that, if I add 1 to both sides, right, that gives me 2 equals v2 prime. So this little guy here, right, is receding away with a velocity of 2 meters per second, okay?
Okay.
So that's basically what this is saying, okay?
All right.
Do you understand?
I think so.
Think so? All right, well, let's try doing a more complicated problem. And we'll make it a relatively simple problem. So we'll consider a ball with mass equal to 2, and its velocity will be equal to 2 also. Meters per second, kilograms if you want. I'm not going to fool around with units. And it's going to collide with a ball that has a mass of 1 kilogram and a velocity, initial velocity, of 0. Okay? And so the question is, what's the after picture look like? Okay, so I've copied the equations that we got for momentum, conservation of momentum, and the conservation of kinetic energy from before that I erased off the board. We're going to use these to solve this general problem here. We have a ball of mass 2 kilograms moving at 2 meters per second, colliding elastically with a ball of 1 kilogram whose initial velocity is 0. Okay?
Okay.
So we're going to plug in for momentum first. So we have m2, which is 1, times v2 prime, which we don't know yet, right? That's the velocity of this guy after the collision, minus its initial velocity, which was 0, should be equal to m1, which is 2 kilograms, times v1, which is 2 meters per second, minus v1 final, which we don't know what that is yet, so we'll write it like this, will be equal to 4 minus v1 prime. Okay?
Yeah.
Now let's use the equation for the kinetic energy that we had. We have v2 prime, which we don't know, minus v1 prime, which we also don't know, is equal to minus v2, which is 0, minus v1, which is 2. So I'd make that plus 2. So this gives us that v2 prime is equal to 2 plus v1 prime. Now I have two expressions for v2 prime, right?
Yeah.
So all I need to do is equate these two, right? If two things are, I can't think of the wording to say that. Well, so if we substitute in for v2 prime this expression here, we get 4 minus v1 prime will be equal to 2 plus v1 prime. Yes?
Yes.
Solve for v1 prime. Oh wait, I made a mistake here. This is not minus 2 v1 prime, this is minus 2 v1 prime. Forgot to distribute the 2 on that. Thanks for catching that, guys. Yeah, so here would be minus 2 v1 prime. So move v1 prime to the right. That will give me 2 v1 prime plus v1 prime is 3 v1 prime equals 4 minus 2 is 2, which means that v1 prime is equal to 2/3 meters per second. Okay?
Okay.
Since I have v1 prime, I can now find v2 prime, right? Because we know that v2 prime minus v1 prime, which is 2/3, will be equal to 2, right? From up here, right?
Yeah.
Which means that v2 prime is equal to 2/3 plus 2, which is the same thing as 6/3. So that should be equal to 8/3. So we now have our final velocities, right? So v2 prime and v1 prime. v2 prime is 8/3 meters per second. v1 prime is 2/3 meters per second. Okay?
Okay.
So we're able to solve this. Now, I'm going to leave it up to you to check whether conservation of conservation of energy, or the kinetic energy, is true in this case, right?
Okay.
So you know what the kinetic energy is before. Since there's no velocity in this ball here, it's just going to be 1/2 times 2, which is 1, times 2 squared, so 4, right?
Yeah.
And that will have to be equal to the kinetic energy of the combined system afterwards, okay? Then we'll let you guys do that now. But that ends our lecture.